Hello everyone, we are Group 14 and our project is Intelligent Spatial Analysis during hurricane events. Our group consists of Kevin, Nathan, and Tahim, and we'll be presenting how our system analyzes hurricane-related tweets to generate meaningful insights. Our project aims to develop a framework that uses locally run large language models to analyze Twitter data during Florida hurricane events. The model determines tweet relevance, topic categories, and sentiment using structured prompts, removing the need for custom-trained classifiers and improving privacy. After processing, the system visualizes trends on geospatial maps, showing how public sentiment and key topics evolve throughout a hurricane. Our proposed solution is the desktop GUI where users can import Twitter data, choose which subsystems to run, and customize parameters such as prompts or predefined topics. The system then generates an interactive geospatial map where users can filter by hurricane event, date range, or sentiment layers, as well as the ability to click clusters to view tweet content and download or export the final map. Our proposed framework aims to accomplish this by building a model that identifies tweets relevant to hurricane events and analyzes their emotional tone using a large language model for sentiment prompts. The process data is then converted into visualizations, including heat maps that use tweet location data to show how sentiment changes across affected areas. Okay, so now we'll take a look at our system overview, where we'll look at the flow of our data through our subsystems. So we start with data pre-processing, where the raw tweets are cleaned and normalized. Next is the relevance classifier, where we filter out the tweets unrelated to hurricanes. And then the remaining tweets are then categorized into different topics. And then the sentiment analysis identifies the emotional tone of our data. Finally, all of the process data is mapped through our geospatial mapping subsystem to reveal trends and activity hotspots.
Hello, I'd like to begin by talking about the data pre-processing subsystem. This subsystem is a very important foundation to the rest of the overall system because if you don't start with good data, then everything else that follows isn't going to produce good results. So the problem we started with was that our data was in the form of very many text files. And this contained a very large amount of data, about 15 gigabytes, for just one hurricane uh, event. So this is hard to directly use in our system. So the goal that we created was to import it into a Postgres database. But trying to do this directly produced an error. You can see the error there. It seemed to be something wrong with the JSON formatting of the data, and initial attempts to verify the JSON formatting and try to import it again, it just didn't work. So the solution that I came up with was to extract only the necessary data from the text files that we need to use for our analysis. And from that, I would build a CSV file that can be imported easily without any error. And here off to the right, you can see all the text files and their contents. So the Python script that I have is this clean tweets.py. The input is all of these text files that are in a folder. You run it from the command line and it extracts specifically the tweet ID field, the created at field, the tweet text, the place, full name, and user location. We need this because we have a unique identifier for each tweet in the form of the ID, which is a bunch of numbers. The created at, so the time, the date and time of when it was, and then the full body text of the tweet. And we have two different location fields because we want to then map the location after we've analyzed the tweets onto a geospatial map. After the, you can see the code, part of the code off to the right. After this runs, it outputs tweets cleaned CSV with all of this data that then was imported into Postgres database. These are the commands into the terminal that I ran to get the database populated with all of the data. As you can see off to the right, the columns that it was supposed to have. And right now, none of the subsystems are using this database. We were just testing with smaller sets of data that we found elsewhere, but the plan is to integrate all of the subsystems to interface with the database. And now moving on to the topic categorization subsystem. In this subsystem, we want to take all of the individual tweets with their full text, and this is very unorganized. There's no way to search through this to really find anything meaningful, right? But if we can categorize them according to their content, such as weather forecasts or damage reports or flooding or anything like that, then we can better look at the data and draw conclusions from it. For example, here are a bunch of tweets, and maybe this one is related to recovery efforts. Maybe some of these are calls for aid and assistance. Some of them are definitely about politics. So how do we categorize all of these? The solution we have is to have a large language model do it for us. So we have O-Llama running locally, and we have a script in Python. Part of it is off to the right here, you can see. It sends instructions to the LLM to label each of the tweets with a generic category in an unsupervised manner. We have another script that has predefined categories. This can also be used, and we're going to experiment with it. But initially, the results from this weren't as desired. We used the Llama 3.21b model and instructed the LLM to only do a concise label, and this really cut down on the time compared to significantly compared to earlier test runs where we were using a different model that was not as lightweight, and we were telling the LLM to do more than just quickly give it a category label. So initial test runs, it was taking upwards of 3 hours for 800 tweets, and we got that down to 3 minutes. This still needs to be improved because this is rather fast, but it's too slow of a process for the millions of tweets that we really want to be looking at. I think it would take like 10 days to go through the 4 million tweets that we have for the one hurricane. So we need to speed up this process. Here's a comparison between the unsupervised version, where we just let the LLM pick categories for each tweet as it saw fit, and the supervised one, where it was given a bunch of predefined topics.
And now taking a look at the components for our relevance classification subsystem, we will have a preprocessed tweet dataset, a locally hosted large language model, a Python interface to communicate with the model, as well as a structured prompt template that helps the LLM determine whether each tweet is relevant to a hurricane event. Alright, so the preprocessed tweet dataset will contain all the clean and standardized tweets that are ready for the model classification. This step will remove noise like URLs, duplicates, and symbols, allowing us to have a consistent input source for our relevance classification subsystem, and ensuring that all the subsequent subsystems receive structured and reliable data. And the snippet on the right is just a snippet from our demo showing how we loaded the tweets that are pre-processed. Alright, so our next component is a large language model, which is the core of our relevance classification subsystem. Instead of relying on keyword matching, our model performs context-aware classification that understands nuance, indirect references, and even sarcasm, which is something traditional models often miss. Because it supports our structured prompt engineering, we can give it very specific instructions on how to decide whether a tweet is hurricane related or not. This makes the model the main decision maker in labeling tweets as relevant or irrelevant, and ensures our pipeline only continues with meaningful data. Alright, so now taking a look at the Python interface, it will act as a bridge between our pre-processed tweets and the LLM. So it will handle the entire communication process essentially by sending the tweets in batches and receiving the model's outputs automatically. So this interface also ensures that our structured prompts are delivered to the model consistently, and it even formats the model's responses so they can be passed cleanly into the next subsystem as we can see on the snippet on the right from our demo. And then this will simplify large-scale processing and keep the entire relevance classification workflow efficient and automated. Now taking a look at our structured prompt templates, which will be a key component that help guide our model in classifying tweets accurately. They help standardize the instructions we give to the model, ensuring that the results are reproducible and consistent across all the tweets. As we can see on the snippet on the right, we give it very clear instructions on determining whether a tweet is relevant or not, and we are even able to specify how we would like the model to respond to us when it finds its results. And by providing this clear context, these prompts help the LLM interpret subtle language cues and ultimately produce reliable labels for whether a tweet is relevant or not. And this makes our relevance classification both precise and trustworthy, especially for downstream analysis. And each component of our relevance classification subsystem was carefully chosen for its role. The LLM enables context-aware classification, which will perform far better than if we were to go with a traditional keyword-based approach. The Python interface simplifies integration, allowing for automated batch processing of our large datasets. And locally hosting the LLM ensures privacy for users and avoids potential API rate limits, which was a concern coming into this project, and allows us to customize our prompts as well. And then finally, using our database to provide a scalable and structured storage solution for both the input tweets and the labeled outputs will help keep our pipeline efficient and reliable as we move into subsequent subsystems. Alright, so now taking a look at our relevance classifier in regards to how it connects to our other subsystems, we can see clearly that this subsystem interfaces directly with both upstream and downstream components because it receives the clean and pre-processed tweets from the data pre-processing subsystem. Then after it receives this data, it then classifies each tweet and then outputs a labeled data set, marking each tweet as either relevant or irrelevant, which feeds into the topic categorization and sentiment analysis subsystems next. And then this will ensure that all the downstream processes work with high quality and contextually meaningful data. And this will, in the end, help improve the accuracy and reliability of our entire framework. So our relevance classification system faces several key challenges, and one of these is facing ambiguous or sarcastic tweets, as they can be difficult for our model to interpret. So to combat this, we plan to refine our prompts with the explicit instructions and examples. And then large datasets also require batch processing and iterative handling to manage hardware limits efficiently. So to ensure consistent classification, we standardize our prompt templates and apply post-processing rules. Limited hardware resources will be addressed by optimizing the model size or adjusting batch sizes. And then finally, unknown edge cases like slang or region-specific references will be managed by continuously updating prompts and reviewing misclassified examples. These strategies help ensure accurate and reliable relevance classification as we move forward. So for the early prototype implementation expectations for our relevance classification subsystem, we expect to be able to connect our Python interface with the locally hosted Olama LLM. And we've actually already tested structured prompts on a small sample of pre-processed tweets to ensure the model can generate labeled outputs as either relevant or irrelevant. And then these tweets will be ready for use by the topic categorization subsystem. Additionally, we aim to establish basic integration with our database to help store and retrieve processed tweet data so that the system can begin handling data flow properly as we move forward throughout the project.
My name is Nathan LaBar, and I'll be going over the sentiment analysis and geospatial visualization subsystems. The sentiment analysis subsystem is responsible for identifying the emotional tone behind each tweet, which helps us understand how people are feeling before, during, and after a hurricane event. The first component in this prototype is the data loader module. The module loads the CSV extracted from our pre-processing steps. For testing purposes, in this prototype, I uploaded a CSV and performed pre-processing before going on to the sentiment analysis component to simulate what this component would receive from the others. In the prototype, due to the nature of Twitter text, we load the data using pandas with Latin 1 encoding to avoid decoding errors. Our sentiment subsystem is fully LLM-based. We use Grok's API to run the Llama 3.1 8B model, which gives us fast inference for large text datasets. Each tweet is classified into one of 6 emotional categories. These categories come from prompts that provide clear definitions and keywords, so the model knows exactly how to interpret ambiguous or emotionally charged language. For each tweet, the model turns both a sentiment label and a confidence score from 0 to 1. This gives us a measure of certainty behind each classification. The analysis pipeline ties everything together. It loops through each tweet in the dataset, calls the LLM to classify sentiment, and tracks processing with a progress bar the user can monitor. As the classifications come back, we store them in a results data frame. This data frame becomes the main output for both visualizations and further subsystems. Once all tweets are analyzed, the subsystem generates a summary of the analysis. We can calculate distribution counts, for example, how many tweets express fear or anger, and visualize them in the charts. We also show sample tweets from each sentiment category. This allows us to validate the system by manually determining if the analysis was accurate. For instance, if a tweet was labeled as fear, it should have been humor. For this subsystem, we carefully selected each component. Google Colab gives us a lightweight environment with no installation needed and was great for prototyping. Grok's API provides fast inference and a free tier. Llama 3.18b had a good balance of speed and language understanding. We chose LLM-based sentiment analysis instead of traditional machine learning models because LLMs understand nuance, like sarcasm, uncertainty, and indirect expressions, without the need for manually labeled training datasets. This subsystem relies on the relevance classification and topic categorization subsystems. In the final system, we will only analyze tweets that are already confirmed as relevant and the data is already cleaned and pre-processed. Once sentiment labels are applied, the results are passed to the geospatial visualization subsystem, which will map these emotions geographically. There were several challenges we needed to overcome, and some we still need to figure out. The Grok API enforces rate limits, so we inserted small delays between requests. However, this causes the analysis to take longer. Processing large datasets can already take hours, so we allow sampling and batching, but speed is still a main concern. Some emotional categories overlap, such as fear and anxiety, so we refined our prompts to enforce clearer rules, but further testing still required. Colab can disconnect during long sessions, so we save partial results frequently, but our final solution will not use Colab. It'll just use the same logic presented. The prototype sentiment pipeline is currently implemented in Colab. We can load the data, configure the model, run batch sentiment analysis, generate charts, display categorized sample tweets, and export the results as a CSV. These outputs feed directly into geospatial mapping. The geospatial visualization subsystem turns sentiment-labeled tweets into interactive maps. We built a web-based interface using Streamlit. The dashboard has three main tabs: Analysis, Map Visualization, and Data Export. The dashboard integrates with the same Grok API and loads the processed sentiment data from here. From here, users can explore trends geographically. The core of the subsystem is the map rendering engine built with Folium. Tweets are plotted on a map using their coordinates, and each point is color-coded according to its sentiment. This allows us to visually detect the cluster's emotional trends. Because thousands of points can overwhelm a browser, we use Folium's Marker Cluster plugin, which merges nearby points until the user zooms in. Clicking any cluster or marker reveals the actual tweet content, giving users context right on the map. To make the system usable outside of a development environment, we created a Windows batch launcher. This script sets the correct working directory, initializes the Python environment, and starts Streamlit with just one click. This ensures the entire visualization tool is simple and accessible for users. We chose Streamlit because it handles UI, state management, and hosting without requiring a full web framework. It lets us focus on functionality rather than front-end development. We chose Folium because it supports different map tile providers, HTML pop-ups, and clustering, which are important for mapping large numbers of tweets. These tools let us build a geographic analysis tool with minimal overhead. The subsystem receives processed data directly from the sentiment analyzer and outputs both visual maps and CSV exports of our processed data. Throughout the process, we've encountered multiple challenges. Having thousands of markers can cause lag, so clustering is necessary. Many Twitter datasets don't include coordinates, so we ensured our demonstration datasets did. Streamlit reruns the entire script on interaction, and we fixed that using session state to preserve the analyses. Performance with large datasets is still slow, so we will need more load testing for extremely large datasets. This subsystem completes the pipeline by transforming our process data into an interactive geographic view.
For the project schedule and timeline, we've already passed the planning phase. We're imminently moving out of the demo test run phase and entering the full subsystem development phase, where we're all going to work on our subsystems, and by early February, finalize that, enter testing, test all the subsystems, fix the bugs, and then beginning at the end of February, we're going to bring them all together, develop a user interface, make it friendly for the end user, and our goal is to be done by March 15th, a little bit before the final due date, to account for any unforeseen delays. And here's all that I just spoke about in a easier to read form. The tasks assigned to us, Kevin Rapkin, am going to be doing the data pre-processing and the topic categorization. Tahim is doing the relevance classification subsystem. Nathan is working on the sentiment analysis and geospatial visualization subsystems. And we're all going to be working together to bring these all together and develop a user interface. Thank you for watching.